We're going to continue in section 11.2. We're going to finish that section up today. We had talked about polygons last time. In fact, let me go back a couple of slides just to remind you where we were. We had talked about 8, I think it is, different names of polygons. Some of them are more familiar to us. We use them quite frequently. We see them a lot around town and things, and some are less frequently used. And then we talked about the fact that we label the vertices in order as we go counterclockwise or clockwise, either way around our figure. We can start wherever we'd like. And that diagonals cross non-consecutive vertices. They connect non-consecutive vertices. This is where we had left off. So we're going to take a look at now is the angles of these polygons. So the way that you say that word is polygonal, okay? Polygonal. You can go with that if you'd like, but that's what you're looking at. It's the angles of a polygon. So there's two angles we can talk about. There's angles that are inside. All right, so those are the ones that are labeled with all the alphas in the picture, right here. I could circle all 5 of them, but I won't. And we also talk about the angles on the outside of the polygon, and those are the exterior ones, and those are the ones that are sort of shaded in blue, and they have these betas associated with them. So an interior angle of a convex polygon, convex means that when you connect diagonals, you stay inside the shape. We talked about that before. Is determined by two sides having a common vertex. So it always meets at a particular vertex. So we don't ever talk about, for instance, I mean, we recognize that there is a point right here, correct? There's a point on that shape. And technically, there is an angle right here. It's a straight angle. That's not what we're referring to when we talk about an interior angle, okay? We're talking about two sides of the polygon forming that vertex or connecting at that vertex. And the exterior angle is the angle that happens when you extend the side of the polygon beyond the shape. So for instance, if we take a look at this shape, in fact, let me erase what I have here just a sec. Louis red. The shape of this it's a pentagon, is actually what's in red here, correct? So every other line or ray or however you want to describe them that extends beyond that forms these angle betas are extensions of the sides. So if I take this side over here up here at beta 1 and I extend it, looking like that, that's what creates exterior angles. Okay, it's an extension of one of the two sides that are meeting there, and it's the angle formed by the extension. All right, congruent segments. Two segments are congruent if they're the same length. We do not use equals. We use this symbol, and I'll say why in just a second, but we use this symbol right here. It looks like an equal sign with a tilde on top of it. Okay, so you've got this tilde shape with an equal sign underneath. That's what it looks like. This means that two segments are congruent. The only time you see the equals sign used is when the two segments are exactly the same segment. For instance, if I were to say AB equals BA as segments, that would be appropriate. They are exactly the same segment. But I wouldn't use that symbol if they weren't exactly the same segment. I'd use the congruent symbol. Signal is not the right word, symbol. So we would say AB as a segment is congruent to segment CD. Those letters used. The way that we mark it in a diagram is we sort of put a hash mark on top of the symbol themselves. So you see those sort of light blue hash marks that are in between there. It's not necessarily that they need to be blue, but just those are sort of to draw your attention to the fact that they're added on to the shape afterwards. They're not really part of the shape. They're just marking that the segments are the same length. So if the segments have the same length, we put those hash marks on them to indicate that in a particular diagram. Right. Same thing's true, but in a slightly different vernacular or description for angles. So two angles are congruent if they have the same measure, right? So if one of the angles is 60 degrees and another angle is 60 degrees, we say that the angles are congruent, right? There is one other way that we could write that, and you have seen your book use it, even on the board I have it written down, is that let's say, for instance, that we're talking about two of the angles in this diagram. Let's use this angle right here, and we will use the angle right next to it. Let me use another color. Right here. Okay, it's now double marked, so it looks sort of a funny reddish purple going on in between them. Those two angles are congruent. How do I know that from my picture? They both have the double hash marks. Do you see that? Okay, so those are two congruent angles. So one way that we could write that is we could write angle, what are my letters? DAE congruent to angle BAE. Okay, they're not the same angle. That's why they say, why do I have C? Not BAE. Did I get the letters in there? Yeah. DAE, BAE. Okay, so the other way that you could see that written, and we won't use it ourselves very often, but if you see it written this way in your book, I'd like for you to recognize that it's okay, is that you could see the little M put in front of it, and it means measure of. So the measure of angle DAE is actually equal to the measure of angle BAE. Okay, so when they put the M in front of it, they're actually talking about the numerical value. Okay, and it is very appropriate to say that 60 equals 60, right? So anytime you see the M in front of it, it's turning it into the actual measurement they're talking about, not the angle itself. Right? An angle consists of more than just its measure. It also consists of where it's located in space and where the rays are starting from and ending, and I mean, not ending, but continuing on to and so forth. That's an angle. The measurement of it is just one piece of its information, right? Like I wouldn't say all I am as a person is a math teacher. It's just part of who I am. I have a lot more about me than just that. Okay, same thing on this. Two angles are marked with the same number of arcs or whose arcs have the same number of hash marks are understood to be congruent. So these angles that I marked over here had the two hash marks, but we also have in this diagram two other congruent angles, right? And they're marked with single hash marks. And we don't have any indication in this particular description how the one hash mark angles and the two hash mark angles are related. They could be related, but they don't necessarily have to be. All right, regular polygons. Regular polygons are the ones that we work with that are nice. They're the pretty ones. They're the ones that we look at and we go, oh, it all looks sort of symmetric and even. Okay? So what do we mean by it for real, though? Well, first of all, it's convex. Okay? So every 2 points that are on the line segments can be connecting inside of the figure. It's equiangular. So equiangular means all the angles inside have the same measure. So you'll see the picture over here where there aren't any hash marks, right? Because they're all the same. So they don't even need to hash mark them. They're just using those arcs. Okay, they're all the same. And then not only does it have to be equiangular, it has to be equilateral. So equilateral means that all the sides have the same measure as well. So if one side's 5, all the sides are 5. If one angle's 50, all the angles are 50. Okay? So that's what it means to be regular. It has both of those features. Now there are some shapes that can have one of those features and not the other one, and it still works. It's possible. But there are some shapes that once you determine that every angle is the same, it automatically makes every side the same as well. One of the shapes that's like that's a triangle. If a triangle is equiangular, it's automatically equilateral. Okay? But if a quadrilateral is equiangular, it does not have to be equilateral. Think of a rectangle. 4 right angles don't necessarily all have 4 of the same length sides, right? So it depends on the shape that we're talking about. If it has to have one, it automatically has both. But if it does have both, we call it regular. All right, so we're going to give it a try now. I gave you an example of a triangle, so I'd like for you to not use a triangle, okay? I would like for you to sketch a polygon that is equiangular, so it has all of the angle measures the same. But it is not equilateral. Not all side lengths are the same. Okay, so no rectangles and no triangles because those are the descriptions I just gave you. And then the second one is to sketch a polygon that's equilateral. All the side measures are the same. But it's not equiangular. And the angle measures are not all the same. So give it a try. But check and see if the person that you're looking at, if you agree with them that it fits the description. So on the first one, that it really is 4 equal angles, 5 equal angles, 6 equal angles, whatever, how many angles it is. All the angles are the same, but the side lengths are different, and the exact opposite on part 2. Just agree or disagree with them. Show them what you think. Okay? Check it out. See if you agree. All right, so I'm hearing everyone, well, not everyone, but I heard several people say the same shape that I wrote down on number 2. So if I heard you and you said it out loud, you know probably who you are. What shape did some of you get on number 2? What did you draw? A rhombus. A rhombus is a really good example on number 2. It's equiangular. Equilateral. It is not equiangular. So it looks like something, and I'm not going to say that I'm going to draw it perfectly, because I probably am not. But that's not too bad, okay? So all of the sides are the same. The angles are clearly not the same, right? We'll talk more about a rhombus later. Rhombuses do have 2 congruent pairs of angles. So the opposite angles are congruent, but not all 4 angles are congruent. And let me draw the first shape that I had mentioned over here, and we'll see if we can create something else that has the same feel to it. This is equiangular, right? Not equilateral. All the sides are not the same. Opposite pairs are the same, but they're not all the same. And so I thought I heard from this group over here something that you could do with some other shape. What did you guys think maybe to do?
You could do an octagon but stretch it out.
That's what I was thinking on this too. So imagine an octagon. So where do you see octagons every day? Stop signs. So imagine taking a stop sign and doing basically what I did with the square. How do you take a square and sort of morph it into a rectangle? Well, you just stretch it out, right? Well, we should be able to do that with any shape that has even number of sides. We can't do it with like a pentagon because there aren't 2 sides that we can stretch along and keep them parallel or whatever. But if we have a octagon, we've got 8 sides, we should be able to do it. A hexagon, we should be able to do it. So imagine taking one of those shapes and just stretching it out. You wouldn't affect the angles, right? You would just affect 1 pair of sides, and you would make it longer. Now, I'm not going to promise that I can draw that one. Let me try and draw a hexagon just because it's got fewer sides. I might stand a better chance. Okay, that's not too bad, okay? All the angle measures stayed the same. They were regular and they had the right angle measures, not as in right angles, but they had the same angle measures to begin with. And then all we did is stretch it along the side. Good job, guys. All right, we're going to turn our attention for a little while to triangles, okay? So this is probably familiar stopping grounds for most of you. You've seen and thought about triangles quite a bit. So triangles are introduced in the early grades, and we talk about them in some of these descriptions there, and then we keep kind of building on it as we go on in mathematics. So one way we can classify triangles is by their angles, okay? So we have acute triangle. And an acute triangle, it means that all three of the angles are acute. What was acute? Less than 90. Okay, so they all are less than 90 degrees. So that's the first triangle you see in the picture. The second way we can classify a triangle is it has one right angle. No, it doesn't say three right angles. That's not possible. But it has one right angle. The other two angles, what are they? Acute. They have to be, okay? So we do have acute angles in these other triangles, just not all three of them. So one right angle, the other two are acute. The third triangle is called obtuse, and an obtuse angle means what?
There's one obtuse angle.
Yeah, so from 90 degrees up to 180 degrees. It's between those two, right? So it's bigger than 90, smaller than 180, and we just have one angle that can do that. And then the other two angles are acute. So no matter what we're doing, we've got at least two acute angles. So you want to be careful that you don't think that you don't have acute angles. You definitely do. So that's an obtuse triangle. Or we can classify a triangle by its side lengths. All right? So the first triangle has all equal sides. It's called what? Equilateral. Good. It's equilateral triangle. The second one only has two sides that are the same length, and the third one is actually different. So what would that one be called? It's isosceles. Well, here the word isosceles meant for another shape later as well. So isosceles means two sides that are the same. And then the third one means that none of them have congruent sides. They're all different, and that one's called scalene. Okay? And you can create triangles that fit one description of the sides and a different description of the angles with one exception, and that exception has to do with the equilateral equiangular issue that we talked about before. Okay? All right, some other other polynomials. I didn't say polynomials. I did. I meant to say polygons. Sorry, polygons. Quadrilaterals. So those have four sides, right? I want to mention a very interesting thing. So let me just say it first. So first we have a trapezoid. A trapezoid in your book is described as a quadrilateral with one or two pair of parallel sides. I want you to write down a note to yourself real quick right here over to the side, real big and bold, circle it, exclamation points. This definition in mathematics is one that is not always used the same way. Your book is telling you it's one or two parallel sides. But there are some textbooks, and there's an example of a page, like in your book, there's actually a page which shows a textbook from a child's book, where the definition that says exactly and only one pair of parallel sides is a trapezoid. Now, the one pair of parallel sides is the ones you think about as being trapezoids. But whether or not it allows or disallows the two parallel side option is up to the textbook writer, to be honest. Okay? So you need to be careful when you're talking about trapezoids of what your book that you're using or teaching from includes or doesn't include. Our book is including a possibility of having two pair of parallel sides. Isosceles trapezoid means that you have two pair of congruent sides as well. And because of the nature of this kind of a picture, right, the one at the bottom, if there are two pair of congruent sides, which two are they? Yeah, it's these legs over here, typically speaking, right? So you're looking usually at the isosceles triangle being these two particular legs. It doesn't have to be always, and I didn't mean triangle, I meant trapezoid. But that's the typical one that we see used, okay, isosceles trapezoid right there. Parallelogram. Now, parallelogram is the reason why most textbook writers and most mathematicians would not like us to use this option right here, the two pair of parallel sides. Because we have another name for something with two parallel sides, two pair of parallel sides. It's called a parallelogram. Every picture on this, I'm sorry, let me step back a second. No, I was right. I was just looking at it wrong for a second. Every picture on here is a parallelogram. They have two pair of parallel sides. Okay? And these pictures, all four of them, are quite different, actually. They have different features beside that, but they do have opposite sides that are parallel. A rhombus has that description too. That's the bottom left and the bottom right hand descriptions or pictures. But they have also 4 sides that are the same. So in this picture down here, if they're rhombus, like you guys mentioned this one earlier, then it means that all 4 sides are congruent. It's equilateral, right? There are 2 shapes that are very special though, and those shapes are squares and rectangles. A rectangle is a parallelogram, right? It is. It is a parallelogram. It's a parallelogram of a very special type. It's a parallelogram with a certain type of an angle, a right angle. So when you have a rectangle, you have a parallelogram where you have right angles. Okay? Parallelograms don't have to have right angles, right? This parallelogram right here doesn't have right angles. It's a parallelogram still, that's okay. So it's not a condition about being a parallelogram. It's a definition about being a rectangle. A rectangle is a parallelogram with right angles. Okay? A square is an equilateral rectangle. That may bother you a little bit. I could give you this shape, and we could all agree, you know, barring anything weird looking in the picture or scaling being off, that it's a square. But it's also a rectangle. Why? Because it's a parallelogram with a right angle. It just has an additional condition to it. What's the additional condition it has? It's also equilateral. Okay? So it's like a more specialized case of a rectangle, but it is still a rectangle and it is still a parallelogram. It is both of those descriptions as well. Okay? So a square is both a rectangle. It's also a parallelogram, but the blank I want to fill in right here is I want to fill in the blank that it's a rhombus. What is a rhombus? Do you remember? What did we just describe it as? Parallelogram that's equilateral. Is that a square? Yeah. So a square is one of these funny shapes that has lots of things we could describe it as. We can call it a parallelogram, we can call it a rectangle, we can call it a rhombus. The most specific name we can call it is a square. But it does fit in the categories of all the other ones as well that we just mentioned. All right, one more shape. This is a fun one. It's not always mentioned, but it is an interesting one. It's called a kite. You guys have probably flown a kite at some point, or at least you've seen movies where somebody's flying a kite or something like this. A kite is a quadrilateral with 2 adjacent sides congruent to 2 other adjacent sides that are congruent. So you'll see all the notation showing this, right? These 2 are adjacent and they're congruent. These 2 are adjacent and they're congruent, and these 2 congruent adjacent pairs connect. And that's what makes a kite. Okay? So you see 2 pictures down at the bottom. The first one looks a lot like the picture above. These 2 are congruent. These 2 are congruent. It's a kite. But by definition, the other one is as well, right? Because notice the definition didn't say anything about convex. This picture's not convex, is it? That second picture, not convex. How do I know? Because that diagonal is outside my shape. It's not a convex picture, but the definition didn't say convex. So this one is also a kite. Now it looks a little bit more like a paper airplane or something like that that's been folded, but it's technically, by definition, a kite. All right, so what I'd like for you to do is I'd like for you to take a couple minutes, go through this list, and I want you to decide if each description is either true or if it's false. Okay? Once you finish all 7 and you feel fairly okay with your answers, I would like for you to compare with someone next to you and see if you got the same answers. If you didn't, talk about it and see if you can decide which one it really should be. Okay? Okay, I hate to stop you guys. You're having great conversations, which are wonderful. So let's have them all a little bit together. Let's start with number 1. Well, I mean, because it's number 1, but also because that's where you guys are sort of fitting a point where I can tell, I can see your faces. Like some of you are like, I'm not sure I'm buying what that person just said. So isosceles and equilateral. It says an equilateral is isosceles. So what does equilateral mean? All the sides are the same. What is the definition for isosceles?
So it is true.
Does it say 2 are the same and 1 is different, Skylar? What does it actually just say? It says 2 are the same. We aren't actually told anything about the third side, right?
Yes.
So does it fit the definition? Actually does, right? Yeah, so that's true. An equal angle is isosceles. That's not a very helpful description, right? I wouldn't want to look at it and say, hey, it's isosceles, but it fits the definition. Okay, how about the second one? A square is a regular quadrilateral.
True.
True, because regular means what? Equiangular, 4 angles that are the same, which a square has, and equilateral, 4 sides that are the same, which a square has. So that one's true. A square is a rhombus with a right angle. True. It's a rhombus, 4 sides that are the same. Right angle, absolutely. All angles of a rectangle are right angles. True. Yes, that is a true statement. A rectangle is an isosceles trapezoid. True. Okay, so and this is one of those ones that wouldn't be true in every book, right? Because trapezoid means that it has at least one pair, so one or more pair of parallel sides. And a rectangle has that. It has 2 pair of parallel sides. And what else did it say? Oh, and it's isosceles. Isosceles means it has 2 sides, at least 2 sides, that are congruent. And a rectangle does have that. Some isosceles trapezoids are kites. That's true. Do you know what it would have to actually be to work? What shape would it actually have to be? What is the most specific description that is an isosceles trapezoid and a kite? A rhombus would work, or a square would work, because a square is a specific kind of rhombus. But you'd need at least a rhombus, the diamond shape that you guys are talking about. Yeah. So it has to be isosceles, has to be a trapezoid, and then it would have to be a kite. A lot of descriptions that are the same. Okay, so yes, a rhombus would work or a square would work for that one. So yes, some are. Not all. That's why they're putting that word some in there. Not all. It doesn't have to work all the time, but it does have some that could fit both descriptions. If a kite has a right angle, then it must be a square. What picture did you draw that made that what you thought? Is a rectangle a kite?
Because they're not adjacent.
Because the adjacent sides aren't congruent. In a true non-square rectangle, it doesn't work. So in order to have a kite that has a right angle, it would have to have 4 right angles, right? It would have to, because the opposite angles are going to be the same. Opposite across and opposite up and down are going to be the same. So you'd have to have 4 right angles. And then the question is, does it have to be a square or could it be a rectangle? And it can't be a rectangle that's not a square, because we do need adjacent sides, 2 of the adjacent sides to be congruent.
So it would be true.
It would be a true statement. So this is one of those slides that makes us all a little uncomfortable because every answer is true. Yes.
It makes you want to put false on.
I know, it does. All right, here is a very nice hierarchy or an organizational structure for our quadrilaterals. I mean, it's got all polygons on here, but the quadrilaterals part's the part that I find to be most interesting. So if you see here, we've got a polygon, and these are not all polygons, but these are the polygons we've talked about so far, namely triangles and quadrilaterals. If it's a triangle, it's either scalene or it's isosceles. If it's scalene, it can't have 2 sides the same. But if it's isosceles, it could have all 3 the same. So this is the description we just had, or the discussion we just had from number 1, right? Isosceles automatically becomes, an equilateral angle is automatically isosceles. Quadrilaterals. For quadrilateral, you can either differentiate that it is a kite or a trapezoid. It has other things too. But if it's going to be in either of those categories, then it has things underneath it that fall underneath it. Trapezoids can be parallelograms, or they can be isosceles trapezoids. They can be rectangles. We've got squares and rhombus in there. This picture is a very nice picture to keep in your mind if you're trying to figure out if something fits. For example, if we talk about a rectangle, we could start with rectangle, which is right here. How else could we describe a rectangle? Well, it's an isosceles trapezoid. It's also a parallelogram. It's also a regular trapezoid, rather. It's also a quadrilateral. Everything above it describes it too. So if we started out with a rhombus, well, a rhombus is also a parallelogram. It's also a trapezoid. It's also a kite. It's also a quadrilateral. Everything above it is a description for it. A less specific description, but a description nonetheless.
So a square kind of fits everything.
It does. It is the character that can hide and disguise in everything. Yes, he is everything. All right, we're going to switch gears just a little bit. We're going to talk about symmetry. I mentioned something a little bit about this. I sort of said it incognito. Regular polygons have this sort of feeling of them being symmetric. Do you remember me saying that? Well, here's what I was referring to. There's a couple of kinds of symmetries, I think 3 or 4 even actually, we're going to talk about today. The first one we're going to talk about is line symmetry. So line symmetry means an object has the ability to have a line drawn somewhere where you could fold it along the line or cut it along the line and create images that are exactly the same. Okay? Not just exactly the same. Fold is probably a better description, but if I have the ability, so here's my hands, okay, my hands. The line of symmetry should be between the two hands, because if I have the ability to fold it and they match on both sides, that's a line symmetry. Okay? So my hands put side by side only have one line symmetry. I can't cut through them like this and flip them down. That doesn't work. Okay? So if you take a look at the image, the first picture, the first image we have, the square, think about drawing, or where could we draw, lines that make a line of symmetry. Okay, so describe one of them for me, Elena.
You could go diagonally.
Okay, and there are 2 diagonals that we could form, right? So we could have this line or we could have this line. Let me do one at a time. Does everybody see that if I fold it along that line, if I think about folding it downward, the top part folded down will be exactly on top of the bottom one. Identical. You won't be able to see any different. Mirror image. Okay, and the same thing happens along the other diagonal. What else could I do? Someone else. Elena mentioned there's more. Up and down. Skylar says up and down. I agree. Any others? Yeah, across. Horizontal line. So this one actually has 4 lines of symmetry. What about a rectangle? There are only 2 on a rectangle. What are the 2 that work? Up and down, so vertical, and horizontal. So let's think about why the diagonals don't work. So let me try and draw one that fits that description that you just had, Elena, this idea of being opposite. So let's imagine that we did the diagonal one here. Oops, that didn't work very well. Let's try again. There we go. If I move it up, it'll work. Hang on. How about that? So if I took the top left-hand corner, or top right-hand corner, and I flipped it down, what would I actually get? Well, I wouldn't get this image down here. I'd actually get an image. Let me see if I can flip it right. I think the image would end up looking like that if it were flipped, wouldn't it? It's easier to actually take, I don't think I even drew it right because I've got too many lines going on in my picture. Hang on, let me move these red lines out. So if I flipped it down, yeah, I did. I just didn't finish my picture. That's what I was problem. So I flipped it, I would get this image like, I don't think I still did it right.
If you fold it,
Here. There's my image I get.
yeah.
I get that image. I don't think I quite drew it straight, but I get the image where it flips down, something like that. This is not drawn
Have 2
symmetrically.
points.
Huh?
Got here.
Yes. The 2 points stay the same, and then the long side flips down, and the short side flips to the side. What's easiest to do when you're trying to figure it out is to really fold paper. If you can draw the image onto just a piece of paper and actually see the fold, that's helpful. All right, so we have 2 lines of symmetry with this one. How about the shape at the bottom? Do we know what that shape is? What's the... It could be a rhombus if all 4 sides are the same. It may or may not be. It could just be a parallelogram, right? What about lines of symmetry for this shape? There aren't any. There are 0 lines of symmetry. Okay, so what we're going to do is we're going to take just a minute. I want you to take a look at 6 shapes, and I want you to figure out how many lines of symmetry. You don't have to draw all of them. If you can count them without drawing, that's fine. If you want to draw them, that's cool. Go ahead and figure out how many lines of symmetry you believe each object has, and then we're just going to call back out what we believe that we have here. So the first shape's a hexagon. Second, we've got the letter A. We've got sort of like a track field on C. Got the letter Z on letter D. And then we've got some interesting shapes with arrows on E and F. lines of symmetry did you get for the first one? 6. So if you didn't get 6, you probably got 3. So what are the 6 lines of symmetry? Well, 3 of them are the diagonals, okay? So if you connect all the diagonals, I'll just draw one of them in there, but if you connect all the, if you have all the diagonals drawn in, there are 3 diagonals. What else do you have for this besides diagonals? Right, through the middle of the sides. So if you did the middle of the sides themselves, it would look something like this. And you have 3 of those that you could draw in, because there's 3 pairs of opposite sides. So we get 6, and there's 2 of them drawn right there. How many lines of symmetry for part B? 1. Right here. Just 1. How many lines of symmetry for C? 2. You should have a vertical one and a horizontal one. That was terrible. Let's try again. That's closer. How many lines of symmetry do you have for part D?
0.
That is 0. There are no lines that can be drawn that will actually flip and make that the same image. How about letter E?
1.
There's 1. Where is it?
In between.
Yeah, it looks something like that, right? It's kind of a funny one, but it does, it works. How about for letter F?
4.
4 is right. So describe to me what 4 we get in case you didn't see 4. What do you have, Elena? You were the one I heard.
From the top to the bottom,
Okay.
cross the other way, and then in between the 2 points, so it'd make an X.
Okay. Almost starts to look like that square that we had on the first slide, isn't it? Yep, that's sort of on purpose. It doesn't just happen. Okay. All right, another type of symmetry is called turn symmetry, or sometimes called rotational symmetry. It's when you're able to turn an object by a certain number of degrees and have a same object you had before. So instead of folding it over a line, you're able to turn it around at one location, a point in the middle usually. Okay. So if you take that first object and you turned it, would it have turn symmetry?
Yes.
Yes. Any idea what degree measure you'd have to turn it by?
60.
You're close, not 60, but you're very close.
90.
90 wouldn't work. No. Do I have it on this slide? Or do I have it on the next slide? Hang on.
The next slide.
I have it on the next slide. Okay, so let me talk through what would happen or how you would make the decision. The one in the middle is the 90-degree one that you guys were saying. You told me 90, but you were looking at the wrong picture. This one's actually 90.
Oh, it would have to have 4 points.
I'm not drawing well. Okay, let's try again. Here we go. This one's actually 120. And this one, 1, 2, 3, 4, is 60. That's what they are. So how do we figure it out? Well, notice the recycle logo. This is the one that we are actually going to focus on. Coincides with itself after a rotation of 120 degrees. Let me talk about why it's 120. How many of the same image is repeated in this picture? It's really 3 times, right? So if I took 360 degrees, why would I take 360 degrees? Because that's what's in a circle. And I divide it by 3, I will find the rotational or the turn symmetry. So we say that this logo has a 120-degree turn symmetry. We could actually rotate the logo by another 120 degrees. So 120 and 120 would be what? 240. So this actually also has 240-degree turn symmetry. We never really talk about an object having 360-degree symmetry because every object has that. It's not very helpful. It's kind of like we don't usually talk about something being divisible by 1 because everything's divisible by 1. It's just not a helpful description. Okay? So how did I get 90 in the center shape, the middle one? 4, because it's 4 objects that are all the same. And you probably heard me up here underneath my breath counting on the last one. Do you see how many objects are the same in that one? It's actually 6. So if we took 360 and divided by 6, we would have 60 degrees for that turn symmetry. Okay, so let's do this next one together. So we're trying to get this finished up. Well, actually I already said this one. So to find the number of turn symmetries for a figure, we divide 360 by the number of similar shapes. So our car tire had a 60-degree turn symmetry because there were 6 of the same shape. We already talked about that one. How many are the turn symmetries? That sounded terrible. How many are? What are the turn symmetries for each of these? So how many similar shapes do we have in the first picture? 5. So what would we do? 360 divided by 5. And it's 360 degrees. So what is 360 divided by 5? 72 degrees. How about this second one?
180.
It is 180. The top shape and the bottom shape, or the left shape and the right shape, however you want to describe them, are the same. And so we would divide by 2 to get a 180-degree rotational symmetry. How about the third one?
60 degrees.
Yeah, so it's 60 degrees. Very good. Now, sometimes a figure will have rotational symmetry, sometimes it will have line symmetry, and sometimes it will both, or sometimes it will have neither. So you can have a combination of these different things. All right. One more type of symmetry today. This is called point symmetry. This symmetry is not always talked about in every book. The last book that I had used for classes like these didn't have point symmetry in it, okay? Just so that you're aware. But a figure is considered to have a figure that has 180-degree rotational symmetry is also considered to have point symmetry. So this image over here, the Chevy symbol in the middle, that is Chevy, right? I'm not just imagining that, yeah? Okay, that's Chevy in the middle. That one has point symmetry because it has that 180-degree rotational symmetry, right? How about the image on the right, this star shape going on over here? Does it have point symmetry? Yes, because if you rotated the 60 degrees 3 times, it would become 180. So it has this point symmetry as well. How about the symbol on the left? Is that Dodge? Is that what that symbol is? What is the symbol on the left? Why is it familiar to me, but I'm not? No, I think it goes with the car company, actually, but I can't remember. There's some kind of a logo. What is it? I don't know. Maybe. Does it have point symmetry? No. Because if I rotated it twice, I'd be at 144, and if I rotated a third time, I'm more than 180. I don't have a 180-degree symmetry with that one, so it does not have point symmetry. All right. When we have point symmetry, the turn center becomes the midpoint of the line for the segment connecting any point with its image. So if you have the letter Z and you turn it 180 degrees, this point would become this point, right? Okay, so the line connecting them is already a part of the shape. And the point that's in the middle, the midpoint, this letter O, would be the turn center of the point symmetry. The letter H does not have a line actually connecting the two images, right? This one with its image over here. But if you put a dotted line between them, connected them, like a diagonal would, basically, the point that's in the center of that connection, which is what they've labeled letter O, would be considered the turn center of this point symmetry. So take a look. We've got a couple other pictures on this page. The one on the left, this sort of orangey looking one, orangey yellow looking one, does it have point symmetry? Yes. What would it be its turn center? The middle, right? This place where all of these sort of triangular-ish shapes, they're not triangles, but they're sort of like them, right? Where they meet. What about my oval? Does it have turn symmetry? I didn't mean turn symmetry, point symmetry.
No.
No? If I rotate it 180 degrees, yeah, it does, right? So it has turn symmetry. It also has the point symmetry. Everything that's point symmetry is automatically turn symmetry. So it has a turn symmetry of 180. So this one has the point symmetry. Where would its turn center be? be the center of the oval. So if I were to take any particular point, and it doesn't have to be anything, you know, on the edges. I mean, we might sort of have felt like we should have taken different points than what I just picked. But if I take these 2 points, one of them would turn into the image of the other one when it's rotated 180 degrees. I would connect it with a line segment, and the midpoint of that, which would be the center of my oval, would be my point symmetry. Look at this fun shape. The arrows that are drawn in gray are not part of the shape. Okay, just the orange is the part of the shape. The arrows are showing you where the point gets reflected to if it's rotated 180 degrees. This is not even a connected curve, is it? It's not. But it still has point symmetry. And this one's actually showing you that the point symmetry has a turn center that's not on the object either. The turn center is the origin, isn't it? It's not a part of the object. That's okay, it's allowed. It's an interesting example. All right, last slide for this section. Circles. Circles are beautiful things. They're like the perfect shape ever, and none of us are ever going to draw one perfectly. We're just going to have to be okay with that. We'll talk a lot more about circles later, but a circle has infinitely many lines of symmetry, each of which pass through the center of the circle. What is another name for each of those lines? You're close, not radius. Diameter. Right? Every diameter of the circle, everything that connects 2 points on either side that goes through the middle, will be a line symmetry. You can reflect it over that line, right? Creates 2 semicircles, 2 half circles. All of the circle's lines of symmetry intersect at the circle center, right? Because they're all diameters. All circles also have infinitely many turn symmetries. I can take a circle and I can spin it however much I want, and I still have circle. Doesn't change anything. So a circle also has point symmetry. Why? What was our definition of point symmetry?
It has turn symmetry.
If it has turn symmetry of exactly 180. So does a circle have turn symmetry of 180? Sure does. So it has point symmetry as well. What would be the turn center? Yeah, the center of the circle, right? Yeah. All right, and we're going to stop there today.